Hi everyone, welcome. Today we are going to be looking at log normal VAR, value at risk, when the prices of the variables are log normally distributed. So this typically applies to your stock, commodities, options, and we have this in your CFA Level 2 and also in your FRM Part 2 in market risk measurement. So we will today look at the equation of log normal VAR and how to derive it, what are the assumptions behind it, and then solve a simple question to calculate the log normal VAR, all right? So the equation itself, if you think about the log normal VAR, the way to compute the log normal VAR is given as your stock. I'm going to use S, you can use P, whichever notation. I'm going to assume that this is a stock. So the VAR is given as the price, the current price of the stock, multiplied by 1 minus e to the power, the mean geometric return value, minus z, the critical value, the z-score corresponding to that particular significance or confidence level, multiplied by the standard deviation of the logarithmic returns. So let's write down this equations. So your S is your portfolio's value or your stock value. I'm using stock, but log normal VAR is applied to any asset class that can potentially have logarithmic returns. That means it cannot go negative. It has to, the lower bound has to be 0. Current portfolio value. Maybe just to make it clear, I'm going to put in a subscript 0 there as 0 current portfolio value. And your mu is the mean of that logarithmic returns. Your sigma is your standard deviation of those returns. And the Z is the z-score corresponding to that confidence level C. Okay, now we will start deriving this. First, make some of those assumptions that are required for this. So let's say my stock at time t I want to see the growth from S0 time 0 to time t. And let's say this change, right? Is time t. Now, the return in this period, we know that this stock is having logarithmic return. So my return is going to be given by a natural log of ST by S0. Now, if there are any dividends, it's not there in the case of commodities, but if the stock, maybe there are dividends, the assumption is that we are going to be reinvesting that. So the return is the ending value of the portfolio, which could be the stock value plus the dividends reinvested divided by the initial value. Then you take a natural log. So that's your return for the time period T. Now this return, if this is this ST, the stock is having logarithmic returns, the value of this stock is going to have a logarithmic distribution, then this return obviously has to be normally distributed. So I can say that return is given by a normal distribution with the average mu and the standard deviation sigma, which means my stock is logarithmically natural log distribution, distributed logarithmically. Now let's go about and think about the VAR definition. So VAR, as we know, is a loss metric, what we usually use to say that this is the confidence level up to this point, this is the maximum loss. So here we are assuming that the stock is logarithmically distributed, which means it's a bound on the left side at 0. Now what we are trying to understand is this value, right? What is this cutoff? What is the maximum loss? You can also think of VAR as the loss metric where it is going to be more than the VAR in the significance zone. So in the confidence zone, the loss is going to be less than the VAR. In the significance zone, in the, let's say 5% is my significance, in that 5%, the loss is going to be more than the VAR, right? So we can write this mathematically like this. So what I want to do is I'll say my VAR value, so this computation would be this loss value that I'm calculating is going to be greater than this VAR, right? And this is going to be equal to my significance level alpha. Now this loss, so VAR is a positive, we usually express it as a positive number. So what I'm going to say is minus, so the loss ST is going to be lower than S0. So I want to put a minus sign, is going to be greater than VAR, right? So this probability is equal to alpha. Now, if I want to remove that negative sign, we are going to change the greater than to less than, right? I'm inversing everything. So it's going to change like that. Here, this ST minus S0, let me bring this S0 here. So because I want to isolate the ending value. So let's say ST is less than, and I want to say this as, so if it goes inside, it is going to be S0 positive minus the VAR. Yep, makes sense. So this is probability is equal to alpha. Now here you can see this S0 minus VAR, right? We are comparing it to ST, right? So that part we are comparing it to ST. So, but this one, this ST is logarithmically distributed. So, but I want to maybe make it into a normally distributed. So I'm going to express it as S0 multiplied by E to the power RT at time t. Okay. And this is going to be less than my stock value, initial current value minus the VAR. The probability of that is going to be equal to still alpha. Okay, this is great. Now what I'm going to do is maybe to take out this S0, remove it. I'm going to divide this equation by S0. So we will get probability of E to the power RT less than, I'm dividing both the sides by S0, 1 minus my VAR by S0 is equal to alpha. Now after this, what we can do is to remove this E, I'm going to take a natural log, so probability of ln E to the power RT less than 1 minus R by S0 to alpha. Does that make sense? Okay, so far so good. So this is going to get canceled out. So if we do this, it's going to be probability of RT less than natural log 1 minus R by S0 is equal to alpha. So in this equation, this part, this 1 minus VAR by S0, this log normal of that entire thing, we can say is that a return R star, so which is the minimum return. Like anything lower than that is going to be in the significant zone. So you can say that this return, which is obviously normally distributed, we had this assumption of this being mu, and the standard deviation of this is sigma. This return R star is such that anything less than that is the total lost value. So this R star, now this is a normal distribution, so we can just write like our usual, this is your left tail. So if I have my return, average return as mu, then I'm just going to subtract the z value, the critical value, multiplied by the standard deviation. And we know that this is equal to your natural log 1 minus from here divided by S0. So now I can write, so this is where we stand. Let's remove this log normal. So after this, you will just have to exponentiate both sides, and my var is now going to be given as S0 multiplied by 1 minus e to the power mu minus zc multiplied by sigma, which was the equation which we wrote previously, right? So 1 minus e raised to the power mu minus the critical value of that confidence level multiplied by the standard deviation. So we have arrived at this equation. This is my log normal var. Now let's look at a question that's just an application, simple question as an application of this formula. Let's say we have a stock portfolio, initial value is 100 million, and the standard deviation annualized is 12%, and the standard deviation is 30%, and the mean is 12% annualized. What is the one-day VAR, one-day log normal VAR, assuming 252 trading days? So that's a pretty standard assumption for the number of trading days. If they have given, say, 250, that's also fine. You can round it to, in case they don't say, you can round it to 250 also. But let's do this simple question here. Let's substitute in this equation. And before we do that, they are asking for a 1 day, and these numbers are all annualized. So we need to make it daily value. So let's start with the return, mean return, mu, which is 0.12 for a year. So now for a day, it is going to be 1 by 252. For a day, it is 1 by 252. So let's do that math. 0.12 divided by 252. That gives me 0.000476. I'm going to store it in on memory slot. So that's my mean. Now let's go into the standard deviation. Standard deviation is 30%, 0.3. Now to convert standard deviation, you have to multiply it by 1 by square root of t. So 1 divided by square root of t is 252. So 252 square root, inverse of that, multiplied by 0.3. And that comes to 0.0188. Store it in another memory slot. Now let's substitute this in our logarithmic VAR equation. The price was 100 million initially. So 100 million multiplied by 1 minus e to the power mu. Mu is that value 0.000476, right? So minus this critical value. So they have not mentioned, I'm going to assume this is a 95% confidence, which means our Z value is going to be 1.645 minus, so I don't have space here. I'm going to make some space there for that. Minus 1.645 multiplied by the standard deviation, which is 0.01889. So it's much easier to do this with a calculator. So I want to do that 1.645 multiplied by recall 2, store this in another memory slot. Now, recall 1, which is my mean, minus that value we stored, and that is giving me minus 0.03. I want to again store this in one more memory slot, and then we're going to take a e to the power second, e to the power 0.698, again store this in one more memory slot. 1 minus recall that, and that is giving me 0.03014. Okay, this multiplied by 100 million. And the answer is 3,014,760. So my var is 3,014,000. I'm rounding it there. So this is my logarithmic var for this values. Hopefully you understood this. If you have any questions, let me know. All the best.